The floating identity. You may know that we have a patented symmetric key encryption algorithm that uses something called the floating identity. Well, though original and elegant, we have just discovered that the floating identity is ultimately not necessary for the decryption calculation as previously thought and stated. Yes, the floating identity that scaled matrix encryption and was once considered the backbone of decryptions, even capable of undergoing recursion and only requiring the digital root to be divided, is being replaced. What went wrong? It had been 2 years since I developed and began using the floating identity. I knew it was necessary based on my knowledge at the time, but recently I realized I wasn't sure if it was truly necessary or whether there was another solution that had escaped me. I had said it was necessary in recent videos, but realized I wasn't positive about that and wanted to test the statement to be sure. I removed the elaborate floating identity logic and replaced it with plain old n divided by 9, and the result was overflow error. I thought, this seems consistent with what I was expecting. Let's get some good advice. Like Neo, I consulted the oracle, and as is so often the case with such endeavors, I was not disappointed. The oracle said to try using the floor division operator, invoked in Python with just 2 backslashes, that always returns the whole part of the quotient, disregarding any decimal remainder. That's all? But that's so simple. Why didn't I realize this sooner? Well, the CBD functions were originally designed to count decimals, so from the very beginning of coding, I was introduced to rounding error and quickly learned to avoid it. After my initial progress, I suppose I adopted a shoot first and ask questions later approach to any procedure resulting in non-integer and/or scientific notation. It took me learning PowerPoint and rethinking my axioms to realize that while the floating identity works, only the decimal part of n over 9 is affected by rounding error, but that's the part that's discarded when rounded down by the for function, strongly indicating that if the whole part of n could simply be divided normally, somehow, that the floating identity may be bypassed. In the old days, I didn't have ChatGPT to help me with such questions. If I didn't know something and couldn't find it on Stack Overflow, I just had to wing it, and that's what I did when I derived and implemented the floating identity. So, to weigh the merit of the floating identity, on the one hand, the floor division operator proves that it's unnecessary. It's not the only way to skin a cat. It's inefficient, as the alternative is much faster. It's cumbersome, an overkill. It's more demanding on the system and slow, and it needs recursion at the highest level, further compounding system demands. On the other hand, it's sufficient. It does work. It's obviously true and clearly number theoretic rather than syntactical. We could say that it's elegant and original. It's novel and has implications on the theory of information science. Though its merit may be great, the cons outweigh the benefit of using it in practice, and it must therefore be replaced as the primary technique for returning data. When I said before in a previous video that matrix encryption was unique for being a rational-based encryption bravely defying decimal rounding error, and that the floating identity is necessary to divide large numbers by 9 meaningfully, I was confused because simple floor division deals with rounding error, so matrix encryption isn't unique in that respect, and it was never the goal of the floating identity to preserve the rounded decimal expansion of the quotient, but only to preserve the whole part of the quotient, which the floor division operator already does. As is clear from the overflow error we observed, what the floating identity actually accomplishes in essence is an alternative way to do floor division by 9 in Python that overcomes the large float overflow error and the scientific notation error. Because the floating identity is mostly recursive addition, and the part of n that gets divided is much smaller than it otherwise would be, via only needing to divide the sum of digits by 9. And then the recursive floating identity is even stronger, only needing to divide one digit, the digital root, by 9, which can never lead to overflow or float representation error. So I implemented the one-line operator solution, and it worked. No more long decryption times, but only lightning-fast decryption times. A great improvement. The floating identity served its purpose well, adding novelty to my patent application and allowing the algorithm to be scaled. It bore a tremendous workload and supported many upgrades beyond itself until it was eventually outdated. It gave matrix encryption its name or identity because of the digital rain-like printout produced. This is something that we covered in our most recent video, and a link to that will be in the description. Will the floating identity be retired? That's a good question. No, far from it. The floating identity won't disappear from matrix encryption, but will be available in certain vintage versions for users with a taste for nostalgia. Strength doesn't come from the things you can do. It comes from overcoming the things you once thought you couldn't do. Matrix encryption is no longer encumbered by unnecessary complexity and is now stronger than ever and ready for the next battle. Next time, a demonstration showcasing our newest software update, holographic character mapping, also called iridescent character mapping.